Okay. Hi everybody. So this is going to be another one of these kind of Verilog instructional videos. Again, I don't really have a plan for this. I'm trying to keep it really casual, mostly just experimenting with whether I like this format and how best to do this. I do want us to talk about some useful and interesting stuff today and kind of continue with the theme um, of, like writing. Yeah, it is. What is Verilog? And what is hardware? Oops. Sorry, I'm still getting used to this software, unfortunately. It's a bunch of really odd behaviors, and I don't really get it. What is hardware? You know? So, my plan for today is to do something very simple. Um, and I don't actually yet want to get into the question of, like, what is hardware? Let's just ignore this today. I want to do just a really simple um, answer of what is Verilog. I want to answer just one really short, simple thing. And the thing I want to talk about is among all the things that Verilog is, Verilog is a software. Yeah, see, I don't quite know how to hold this pen correctly. That's the problem. Software language. That's the thing that people don't. It might sound surprising because Verilog, you think of it as a hardware design language, and it is a hardware design language. It is not primarily a software language. Um, so I should probably say that, not primarily. Uh, but Verilog, is actually a somewhat functional software language. You can go and write software in it. Nobody would suggest this to you. It's not a good idea to do it. Uh, but it does have all of kind of the basic features that you think of in a software language. You can, read and write from the command line. You can open files. You can manipulate files. You can write text back. You can, make for loops over, your variables. You can do stuff like that. All of this would be, annoying. It would be annoying to build a big complex piece of software in Verilog, of course. Um, but I think that's kind of the question, it's just one thing that I want to talk about first because people get in their heads like, I can't even pick Verilog up. I can't do anything with it. And the thing is, you can do a lot with it. You shouldn't do any of it with it. You shouldn't do any kind of software development with Verilog. Um, but you can. So that's kind of what I want to talk about today. I want to just give a very simple example of, showing that among all the other things that Verilog is, it does have this software component. Uh, and maybe the core of, the underlying conceptual thing that we're going to start hinting at here is this like deeper question of just um, what is a language? It's like a much deeper question, right? Because this also could be, and maybe we talked about this a bit last time, but you've got programming, another M there, I promise. So you got programming languages, but you also have hardware languages. You've got things like declarative languages, like something like maybe you could think of something like Terraform if you know what that is. Um, so Terraform is a maybe that's kind of a weird example, but it's a language for setting up kind of systems of machines, systems of resources. If you've used like Google Cloud platform before, you may have seen it, but it's you know, if I specifying a way to um, boot up a bunch of machines and set them up in a specific way. Um, and so there's all of these things that could be considered languages. Um, and you know, the underlying thing that I want to talk about is you know, what really makes a language and what is a language for? And the answer, unsurprisingly, is really broad. Languages can do all types of things, and a lot of different things are languages. And I think the thing that's really interesting with Verilog specifically is usually languages kind of have, they're really meant to do one thing. Like if you have Python code, it's meant to be run through the Python interpreter. Verilog is a language that actually is meant to do many things. Um, and again, this is where this starts to get interesting, because the answer to what is a language is really determined by the tools that consume the language. So when your Python interpreter consumes Python uh, and interprets the Python, it kind of gives definition to the Python code that you wrote, right? If you deleted every Python interpreter off the face of the planet, there would really be no meaning to all the Python code that you've ever written. It just becomes meaningless. There's no thing that defines what it does anymore, or there's no thing that, you know, gives it meaning. Maybe you have the Python spec that gives it meaning, right? But it's not an executable. It's not an executable thing. So I think that's the really interesting high level concept here, that I want people to take away, is that languages are really determined by, or really defined by, the tools that process them. Sorry, I'm just checking the stream, making sure everything's working. Okay. Yeah, so that's the kind of the high-minded idea that I would love people to take away here. And so Verilog is interesting, and we're going to keep touching on this because Verilog has a lot of different tools that can interpret it and that can give it meaning. So the same Verilog, the same piece of Verilog can, you know, the same file on your machine can separately go into a tool flow that turns it into a silicon chip, so actually produces something physical. It can go into a tool flow that produces a bunch of ones and zeros that get pushed onto an FPGA and program the FPGA. So not necessarily something physical because the FPGA already exists, but some, you know, binary code that essentially programs the FPGA to do what you want. And you know, an even different route, it can go through a simulator and just produce executable code on your machine that can simulate what the hardware would do. And so that's, you know, at the highest level is already three different, completely different routes, three different routes from the same file that produced completely different meaning. Like, how do we compare the meaning of a simulator executing your Verilog code on your machine versus a taped out piece of silicon? Those two things are kind of incomparable in some sense, but we can compare them because we can say, you know, the behavior that I'm simulating on my machine is the behavior that you would see from this chip if we powered it up and gave it the same set of inputs. So that's, you know, I think that's one of the main reasons that Verilog is so conceptually strange, is because there's so many tools that give it so many different meanings. Um, and often these tools, often they differ as well. Like two different simulators might have two different behaviors over Verilog. And this is a just kind of yet another pain point that makes Verilog so confusing and painful for people. But so let's get back to this. You know, let's just do the really simple example. So like, you know, the really simple example I want to show today is just that, you know, uh, of all the things Verilog Verilog is, it is also a software language. So then the question is, you know, if I was saying that, what gives a programming language or a language meaning is the software that processes the language or is the tool that gives the language meaning. Um, we can ask what tool makes Verilog a software language. Sorry for these weird scribble artifacts. That's not intentional. And the answer here is a simulator. I already mentioned it, but a simulator. So a simulator is something that is in theory supposed to take your Verilog hardware design and simulate the behavior of that hardware design just, on your machine. And so when you're testing out your design at the earliest stages, you can, test out the functionality just on your machine itself. The thing is, Verilog has more than just the hardware parts of the language. There's more than just, describing hardware behavior in Verilog. There are plenty of other features because Verilog was actually originally a testing language, a language for producing kind of test suites to test hardware with. And so it looked a lot more like a programming language. And so those features are still there, and a bunch more have been added. And so because of that, you can write purely the software subset of Verilog and run it through your simulator and get out something that just looks like a piece of software. So kind of to put this simply, like a Verilog program / design with only software code, i.e., no hardware description, is just a piece of software. I'll apologize again for my handwriting. I should have said that at the top, but my handwriting is really bad. That's just always how it's been, and I'm not used to this tablet, so it's especially worse. Um, it's especially bad with the tablet. Okay, so this is kind of. Oh, didn't mean that. Uh, this is kind of the key here. This is kind of the thing I want to show today. Is that of all things that Verilog is, it is just a software language. We can just write pure software in it. You shouldn't do this, but I'm not doing this because I think you should do this. I'm saying this because I really want to kind of lower the barrier to entry for playing around with Verilog. And I think a lot of people kind of hear about Verilog and they're immediately like, well, I can't do anything with it because I can't make a chip and I don't have an FPGA. I don't even know what an FPGA is. I don't know what hardware is. And this is just to say, like, this is to show you, no, you can go download Verilog now, and not even download Verilog. You can go download Verilator, which is the simulator we're going to be using. It's open source, it's free, and you can run a Verilog file just very quickly, very easily. So that's what I want to show you today. Okay, so let's switch over to Visual Studio. So I'm here in Visual Studio. I'm in VS Code, and I'm gonna just do this all live. So I have this Git repo here, but there's nothing in it, and we're just gonna do this from scratch. So sorry if it's slow, but like I think it's, I didn't really want to do any setup. I wanted to keep this kind of low barrier to entry, and you can just walk through this with me. And we're also gonna kind of make this somewhat experimental because I've been using OpenAI Codex a lot, and so we're gonna do a lot of this with Codex. Um, I'm not gonna talk much about AI. You all can have your own opinions on AI. Luckily, I've had, a long career of doing software engineering before this, so I know how to write code. Um, I love these AI tools. I find them incredibly useful. I'm not going to blanket advocate for their use. Um, you have to know what you're doing with them, but um, maybe I can kind of show you my process here and show you how they've been useful to me, and that can all, also be part of the interest of this video. So what I really want to do is I want to set up kind of uh, a simple Verilog hello world. Um, and so, we can just ask Codex to do that. Let's set up a simple system Verilog. So system Verilog is kind of the current correct name for the language that is Verilog. It used to be a separate version of Verilog that had more advanced features, made it easier to do like large scale, more interesting testing. As far as I know, pretty sure this is correct. Verilog and System Verilog are now just the same thing. The Verilog standard became the System Verilog standard, or maybe vice versa. They kind of just said, everything that's the System Verilog that is now Verilog. So these are one and the same. So let's set up a simple System Verilog. Hello world that simply prints a string to the console. Set up a compilation script, or set up a simple shell script to compile and run the software or the program with Verilator. And so, like I said, Verilator is an open source simulator. If you're on Mac, you can do brew install Verilator. I've already got it installed, so I won't do this. Just make sure it's on the, yep, so it's on the path. Um, so Verilator is great. It's a example of a really powerful piece of open source hardware tooling. Um, it's kind of a model of open source hardware tooling out there. Highly recommend it if you're, just trying to get into hardware. This is a really good way to, you know, you can do all of your functional testing with Verilator, especially as you're just getting into hardware design. Um, it's very well documented. They've got very active support on GitHub, so whatever you need, you should be able to find. Okay, great. So let's see what Codex did for us. Um, so it looks like it, put in the simple design into this hello.sv, and we'll take a look at that in a second. And it also gave us a run Verilator script. So that's awesome. Why don't we just go ahead and look at this hello world? And so, yeah, this is perfect. So this is maybe the simplest Verilog that we could have written. I mean, even simpler would have just been to delete that line. In fact, we probably could have just written this, and it would have been legal, potentially. Um, so why don't we just do this for now? And this is kind of like maybe this is the true hello world of Verilog. And so the first thing you're going to see, let's just talk about maybe the three most important things here. First, this module declaration at the top. So everything, well, most things in Verilog you can think of as modules, and modules are really like hardware blocks. So it's kind of weird that we're defining our software inside of what I'm calling kind of a hardware block or a hardware design, really. But again, this is mostly a hardware language, so you shouldn't be too surprised that we're kind of grafting this on, or we're kind of, abusing the system in a sense. So normally these modules would generally would describe like a hardware block. And so we've got this hardware block or this module called hello. And then inside of this block, we've got this initial. And this initial, it is what it sounds like. What it's saying is essentially initially at time 0, you're going to do anything inside this initial block. And when I say block, I mean before you saw that there was this begin and an end. And these are kind of the curly braces of Verilog, begin and end. It's very odd, but you can just read it as, as open brace, close brace. Like this is what this means. It's just an old school language, and so, the norms of curly braces maybe weren't in place at that time. And so this initial block, everything between this begin and end, is going to run at time 0. And we're not going to get too much into, the nature of time in Verilog, but just again know that it's a language for hardware, and so when you're talking about hardware, time becomes incredibly important. The timing of different events, and Verilog is really all about events and synchronization of events. And so in this, kind of time-based programming model, initial means exactly what it sounds. At time 0, do these things. Great. So then you see this dollar sign display. Dollar sign dollar sign usually indicates some kind of like function call, or maybe like a system function call. And so display does exactly what you think. It's just going to display something out of the command line. So all in all, when we, quote unquote, run this piece of software, or when we like simulate this hardware design, um, this simple hardware block, we expect it to just print hello world to the command line. Okay, so let's go back to codecs. The other thing that it gave us was this, run verilator file. So what is in this file? So this is just a really simple script. We're going to just do some kind of setup here at the top. And then we're going to define the hardware design, compile it, and run it. And let's just go through this. So the main, thing we need to look at here is this verilator invocation. You don't need to know all this stuff by heart. This is kind of something you can just copy for yourself. But what this is doing is essentially it's compiling our source file, which in this case is hello.v. If you kind of expand out this this variable definition, it's compiling this source file into a binary. And that binary is going to just be named whatever's this top variable, in this case hello. And so there's some options here. There's this W all option. This is actually just turning on all of the warnings so that so that Verilog Verilator lints our code, checks that our code makes sense. This is really important in hardware because it's very easy to make small errors that other tools don't necessarily catch. So Verilator is very good at catching these very small, weird inconsistencies that can lead to bugs or unintended behavior down the road. And then binary is just telling Verilator, turn this into an executable, turn this into a binary that I can run. There's other things you can ask it to make. You can just ask it to make raw C++, for example, instead of compiling it. So this just asks it, tells it to turn it into a binary. And then this line actually runs that output binary. So in general, Verilator always outputs things to this object directory. And inside of that, we're going to have a binary that is named top, because that's what this O command here, or flag here, specified. Okay, awesome. So we should now just be able to run this run Verilator script. Let's just make this executable, and we're going to run it. Okay, so you'll see Verilator is running here, and under the hood, what Verilator does is it turns the Verilog into C++, and then it compiles that C++. So if you want to look through these commands, you'll see that's exactly what it's doing. It's creating C++, and then it's compiling it, and then it actually, because we call the binary here, it runs it. And this is actually, this is the first case of me being wrong, first of many cases, probably not even the first in this video. I'm sure I was wrong already. But the thing I was wrong about was the fact that you truly actually do need this finish command to tell Verilator to essentially stop the simulation, because like I said, this is simulating hardware. It's not just running straight line. While we're kind of hacking it in a way to make it just run straight line code, that's not the intention. It's really to simulate this kind of event-driven system. And so you need to explicitly stop your simulation at a certain point. Because otherwise, it may want to keep running. It can keep running, basically endlessly, potentially, and simulating new events. And so you have to explicitly stop it. Okay, so that's what this finish does. So why don't we go ahead and rerun it, and you'll see Now that we have the finish, we recompile and we hit this finish, and we do in fact print out this hello world. Okay, great. So that's the first thing done here, and that's great. But we want to do something more interesting, right? Like, so now you can see that it is a programming language, right? You can run this from the command line. All you have to do is type these 6 lines of code, and you can just invoke this command, install Verilator with Homebrew or whatever, and invoke this command and run this. Oh, by the way, if you're on Linux, if you're on Ubuntu, the Verilator version is pretty old. I would recommend just installing a pre-built Verilator from their GitHub page, um, or you can go to OSS CAD Suite. It's the other thing you could look up. OSS CAD Suite. This is a kind of a pre-built suite of open source hardware design tools that will have Verilator inside of it, and it'll have an up-to-date Verilator. Okay, so now we want to do something more interesting, right? Like, we show that we can output, but the classic example of testing out a software language is, or one of the classic examples is like, can you build like a grep-like tool? And that will kind of really prove the fact that that you can do something interesting with this language. And this is the kind of thing that in the past I would have had to write up myself. And I have written a version of it, but I won't necessarily be able to write it by hand now. That would take some time. But this is also great, a great thing to apply something like Codex to. And again, this is kind of where you need to have you need to be able to think for yourself when you're using these tools. You need to be able to say, like, here's the thing that I want, and here are the features that I want, and you have to be able to give a good description. But in this case, we can pretty clearly describe what we want to do. So let's just ask for a very simply featured grep-like tool. I would like you to implement a very simple grep-like tool in Verilog. You can reuse the hello.sv file. You may rename it if you'd like. Make sure to update the run script as well. So now let's talk about what we want this simple grep-like tool to do. The grep-like tool should take a directory path and a pattern. The pattern should be very simple. It should be a very simple subset. Let's say the pattern language should support a very simplified form of regex. For now, just say we just support dot. That's a pretty easy. Just support the dot operator, and then the dot. That's a fairly simple thing that it hopefully should be able to support. What else? What else should we say about this? And then maybe just make sure to test the program yourself. Make sure to test the program yourself. Create a few simple test files and test some simple patterns. So I have no idea if this is going to work, by the way, just to be clear. This is the kind of thing that I think should be able to work, and I think Codex should be able to figure it out based on the things I've asked it to do before. But we may run into issues here. Either way, it's worth experimenting. Um, so let's go ahead and run this, and maybe while it works, I'll just talk a little bit about um, using these AI tools and things that I've run into using them. Um, so I think your mileage may vary. I think if you don't want to use AI tools, I fully encourage you not to. I don't want to come off like a massive advocate and you know worshiper at the cult of at the altar of AI. However, I do think these tools are really helpful, and I've had a lot of friends tell me that they can't quite figure out how to um, make them do what they need them to do. Uh, Essentially, it seems like they kind of just fail. They kind of fall flat on their face. And I found that, of course, it's all in the prompting. That's obvious. It's the only way to give input to these things. Um, but I found, uh, kind of one key to this is essentially just giving it the tools to solve its own problems is often useful. Um, in this case, you'll notice that I said, make sure to test the program yourself. And I didn't give many details here because just in my experience, it's going to know what that means. But I really mean, compile, run it with Verilator, look at the output. Is the output what you expect? Do a bunch of iteration. It's getting smarter and smarter. It kind of, in the past, I've had to handhold it through debugging processes, but I've had it do very complex debugging routines very successfully. Um, so that's part of the key here. So let's take a look at what it's doing. So, and seeing the thought process is also useful. It's useful to see it, is it on the right track? This is quite a fun puzzle. I'm figuring out how to build a simple grep style tool, mainly in system Verilog that reads files and matches patterns. By the way, this thing cheats a lot too. That's another thing to think, to realize. So like I can already tell it's probably gonna cheat because I think it's gonna just try to call things on the command line, which is not what we want. Um, or maybe doing that. Um, okay, so what's it doing here? It's making some functions, and yes, there are functions inside of Verilog, and that they really do mostly act the way you think that they do. There's some, uh, eh, they're not necessarily exactly the same as software functions, but they can be. They can be pretty close. Um, So it's also doing a pattern matching. Okay, nice. It is implementing this pattern match kind of directly. And I'm not checking to see if this is correct right now, but maybe we can just scan through. So uh, getting the line length, getting the pattern length. If the pattern length is 0, then just return 1. So I'm assuming that means that that just matches right away. Um, if the line length is less than the pattern length, then the pattern length can never match. Or the pattern can never match, and so you return 0. That's great. And then we're going to just uh, iterate for line length minus pattern length. So you don't have to iterate over the whole string. Very nice. And then we're going to keep going. So we have another inner loop here in which we're looping over the pattern. And what are we doing? So this is the pattern character, this is the line character. And I see, so it's basically checking are these two, so at every point in the string, at every point we're asking, are the characters equal? Um, or is the pattern character a dot? That's what this must be encoding. That is my guess as to what this encoding. And if either of those aren't true, if there's not a match and the thing isn't a dot, then we broke this okay. And if at any point the pattern just fully matched, we didn't break this okay condition, then we can return. Great. That's a really nice, simple implementation, fully in Verilog. Sorry, I didn't even realize I was going to go through that as we were going through it, but we did it. So now let's see what's it doing here. Um, so now, okay, so now it's actually making and the other nice thing about I would say about using AI tools is that you discover a lot of features of languages that if they exist, you may not have known before. It can also hallucinate features, but like this is not something I knew existed. This value plus args. I'm not quite sure what's happening here. I'm not sure if that's just a system call uh, or what, but it looks like it's kind of doing a argument parsing, which is great. You know, that's a nice feature. I didn't know that was in here. Um, and so now it is trying to use the command line, which maybe we should tell it not to. And then we are going to actually, for every file that we find, yeah, so we're going to iterate over every file that we find in a directory, and we're going to do pattern matching on each line. And I'm not quite sure how we're going to return if we're successful there. Okay, so yeah, so sorry, I've kind of went a little long here, but it is interesting. I was kind of getting a little too deep in the details. Um, so now, I haven't actually given it permission to run uh, to run commands. So we can go ahead and uh, I'm just going to give it some blanket permission to do these tasks. Also, if it deletes my home directory in this video, that would be really, really great. That would just be perfect, honestly. Um, but, it hasn't really done anything all too threatening since I've been using it. Okay, so uh, it seems to think that it did it, implemented a tiny svgrep that scans all files under a directory, matches a substring pattern with .wildcard, and prints the file line content. Very cool. The Verilog does the matching and line scanning, while find is used to enumerate files. It's a little bit of cheating, I would say, but it may actually not have a way to get files otherwise. So that's pretty clever, honestly, that it was able to do that. There may not be a way to list directories in Verilog. I wouldn't be surprised. That's not really a common thing you have to do in hardware design, but there may be ways to do it. So grep reads directory and pattern, builds a file list, matches patterns with .wildcard, and prints hits. Run Verilator builds grep.sv and runs it with CLI args. Added sample files under test data. Okay, great. So now this run Verilator script has just been converted into a simple helper that builds and then runs the tool. Just kind of passes it in with the appropriate directory and pattern. That's great. So why don't we use some of its tests here? So test data and then this like hello like pattern. So let's look at these. So hello world, hello world. These are great. This is funny. I like it. So let's go ahead and run some of these. Okay. So down here, we're going to go ahead and run. So we expect this to, pointing at the test data directory, we expect this to match whatever looks like hello. So we should match these first two here. We shouldn't match any hello here, and we shouldn't match any hello here. So let's see what this does. So this runs. You'll see this make line is just saying essentially that the Verilator build that we call and run Verilator here doesn't need to do anything because we already built the binary. But then when we actually run, starting from here is where we actually run the program. And you'll see, yeah, we've matched, these two things, and I can actually click on these and go right to them. So that actually worked. And then, let's do this one as well just to see if it works. And so, we got these two matches. We can definitely do some things that would probably that might break this, like if I just do like ... Okay, that's working kind of. If I do a bunch of dots, I wonder what happens. No match, that's maybe not surprising. If I just do a single dot, that just matches everything. Okay, that's great. If you want to play around with this, like you should try it. I'm sure you can break it. I'm sure there's a bug. That's not exactly, that's not the point here. Um, but yeah, this is great. Codex did a great job here. And now let's kind of come back around to the point. What were we talking about? Why did we do any of this in the first place? Um, and the point here really is that Verilog is, among all the other things it is just a programming language. There is a programming language buried in there somewhere. And I do want to get around to, actually diving into what uh, what the hardware design parts of Verilog is, and that's expansive. There's a lot to talk about there. And what is hardware design? What does it mean to design hardware? What does it mean to take those other paths that I talked about, right? Because today we just took one path. We did Verilog program becomes an executable that we could run, and it's software. But like I said, Verilog has all these other routes. There's the route that goes to an FPGA, maybe a little bit more comprehensible potentially for some of you out there. But then there's the route that goes to silicon. Like how does this text turn into a hardware design etched into silicon? What does it mean to have a function that turns into a silicon chip? Um, so that's hopefully that we're going to get to down the road. Today, I really just wanted to answer the question of, you know, or show you that Verilog, among all of its many features, is also just a programming language. You can pick it up and run it today. You can do useful stuff with it. You shouldn't do that. You shouldn't be writing grep in Verilog. Um, but this is really just to show, that you can look through and see if there's anything interesting here. Um, and I guess I'll end it there. So, one more exploratory stream to see how this works, to see if this content is interesting to people. If there's anything that I hope you came away with here, it's that Verilog is something that you can pick up and run today using only free software. Um, AI tools actually do handle it pretty well. You can probably just ask Codex or ChatGPT to replicate this example. I should put this up on GitHub. I can't promise that I'm going to remember to do it. Um, but if I don't, again, you should be able to just ask ChatGPT to do it for you, and I'm sure it can replicate. So with that, thank you.